Today's lesson is more application of integration. Today we're going to do growth and decay problems. You did these in Algebra 2. You did them in pre-cal. Now in calculus you get to do them using calculus. It's kind of fun. Anyway, one thing to pay attention to, if the problem says something is directly proportional, the equation is, y equals kx. It's directly proportional to x. Okay? Or you can solve for k and have y over x equals k. Today, most of our problems are going to say the rate of change of y with respect to time is proportional to y. Okay? That's what most of ours will say today. Something about the rate of change. If it's inversely proportional, you have y equals k divided by x, or you have xy equals k. That's inversely proportional. So the first thing you're going to do is read the problem. It says the rate of change of p with respect to t. So dt, let's make that a little d, so we're consistent. dp over dt is proportional to 10 minus t. And now we're going to separate our variables like we did yesterday. Since there's no p over there, we just left just dp over here, k times 10 minus t dt. And then you integrate. Well, the integration of this is p. This gives you k times 10t minus t squared over 2 plus c. Right? The rate of change of n with respect to s, so dn ds, is proportional to 250 minus n. Find the function. So we separate our variables. This has got an n in it, so 1 over 250 minus n dn equals k ds. You got to do a u sub here. U is equal to 250 minus n, so du equals negative dn. If a negative out front, 1 over u du equals ks plus c. This is negative natural log of 250 minus n. And you multiply by the negative. So you get natural log of 250 minus n equals negative ks plus c. E to that power, so you get 250 minus n equals c e to the negative ks. We're going to come down here where there's more room to write, and you'll remember why that happens, okay? All right. The rate of change of y is inversely proportional to y. So dy dt is inversely proportional to itself. Separate them, you end up with y dy equals k dt. Integrate, get y squared over 2 equals kt plus c. Multiply by 2, y squared equals 2kt plus c. And now take the square root. So you get y equals plus or minus the square root of 2kt plus c. All right, the rate of change of y is proportional to the square root of y. So dy dt equals k square root of y. Separate your variables. 1 over y to the 1/2 dy equals k dt. Integrate. That's y to the negative 1/2. So you add 1, so you get y to the 1/2. Divide by 1/2, so you end up with a 2 equals kt plus c. You divide by 2, so y to the 1/2 equals kt divided by 2 And now you square both sides. So y is equal to kt over 2 plus c squared. Okay. Many growth and decay problems, the rate of change of variable is proportional to the value of y. So we're going to start with this right here. And I'm going to work it right here. dy dt is equal to ky. You end up with 1 over y dy equals k dt, and you integrate. This is the natural log of the absolute value of y equals kt plus c. And then you raise them all e to that power, right? That was what we did yesterday. So this becomes y. No longer need the absolute value because the range of the e to a power function is positive. So we're good to go. This, remember, it's e to the kt. I'm going to write it down again so we remember how that happened. We just called this the constant. So your equation is y equals c e to the kt. Okay, so that equation, anytime you read a problem where it starts out with the rate of change, it's proportional. This is your equation. Starting value, constant for the whatever's decaying in time, the amount at the end. Remember that pre-cal? C is the initial value, K is the proportional constant. Growth occurs when K is positive, decay occurs when it's negative. Okay, so you're going to separate your variables, integrate, solve for the initial amount, then solve for the other missing parts. So here's our problem. The weight of a population of yeast is given by a differential function. Yt is measured in grams, T is measured in minutes. The weight of the yeast population increases according to this equation, where K is a constant. So that's proportional. At time t, the weight of the yeast is 144 grams. It is increasing at a rate of 24 grams per minute. Write an expression for yk. All right, so you know that it's this equation, y equals c e to the kt. And we also know that y is equal to kt because we said it was proportional. No, dy dt is proportional, right? The weight of yeast is given by the weight of yeast increases according to the equation. All right, so yeast population is 140. So I plug it into this equation. Why did I do that? Oh, I know. Never mind. Sorry. They're increasing at a rate of 24 grams. So we're going to use that, plug it in here. So the rate's 24. Time is 0. K times time. No, ky. The rate is equal to ky. Oh, there you go. Sorry. Man, we're just going to start this problem over. Sorry. So we know dy dt equals k times y. So dy dt is 24 when y is 144. So 24 divided by 144 will give me k. So k is equal to 1/6. Then I know, because it's proportional, I'm going to use this equation. So y is going to equal c e to the kt. I have 144 equals c e to the 1/6 times 0. So my initial amount is 144, which we sort of already knew. So my equation is y equals 144 e to the 1/6 t. And that's your constant for yeast. That's a 6. Okay? During a certain epidemic, the number of people infected at any time increases at a rate proportional to the number of people that are infected at any given time. So the rate people are infected is equal to the number of people infected. If 1,000 people were infected when the epidemic was first discovered and 1,200 were infected 7 days later, then write the equation where there are 12 days after the epidemic. So we know that 1,200 is equal to the initial amount, e to the k times 7 days. First thing you do, remember, is divide by 1,000. And then you take the natural log of both sides. So the natural log, this reduces to 6 over 5 equals k times 7. And then you divide by 7. So the natural log of 6 over 5 divided by 7 is equal to k. And I'm just going to leave it that way. Or I'm going to write this as 1/7. 1/7 times the natural log of 6 over 5. And I'm not going to get a decimal for it yet. Okay? Write the equation where there are 12 days after the epidemic. So 12 days after the epidemic, you know that P is equal to the initial amount, E raised to the K, which is 1/7 natural log of 6 over 5 times T. And you don't even have to do the calculations. They just want to do the equation. All right? Not bad. Okay? Your tires have run over a nail. Air leaks out of the tire at the rate of change of air pressure inside the tire is directly proportional to the pressure. So dP dt is equal to Kp. Evaluate the proportional constant at the time 0 when the pressure is 35 and decreasing at a rate of. So it's decreasing, negative 0.28 equals K times the pressure, which is 35. So K is equal to negative 0.28 divided by 35 and get negative 0.008. Solve the differential equation subject to the initial conditions. So y is equal to the initial amount, e raised to the k, and if you leave it at negative 0.28 over 35, it's always exact, times t. Sketch the graph without a calculator. Well, you know, at 0, it's going through 35, and the pressure's decreasing. It's e to a power, a negative power. That's what your graph looks like. It's going to slowly go to 0, correct? Correct. What would be the pressure 10 minutes after it's punctured? So y is equal to 35, e to the negative 0.28 over 35 times 10. I did the math and got 32.309 pounds PSI. Pounds per square inch. Don't forget your units. AP exam. Lose a point. Don't be silly. The car is safe to drive if the tire pressure is 12 psi or greater. For how long after the puncture will it be safe to drive? Well, that's where you set it as 12 is equal to 35 e to the negative 0.28 over 35 times t. Divide by 35. And then take the natural log of both sides. Oh, when you take the natural log, that e went away. That was the whole point of it, right? 28 over 35 times t. So t is equal to 35 over negative 0.28 times the natural log of 12 over 35. You notice I would leave it that way, and I don't punch it in my calculator until the end. When I get done, I end up with 133.805, and I go, whoa, that's a long time. Remember, this is per minute. Okay? If you turn that into hours, it's approximately 2.23 hours, which is kind of amazing to me that you can drive that long with a nail in your tire. It's just when you get home, put it in the garage, you get up in the morning, it's flat, that you're frustrated. All right. These, I'm going to let you work on your own. I'm going to tell you the answer is B. See if you can get it. And this one, the answer is B also. So work those problems and see if you can get them. And that's all there is to today's lesson. We do need to do a Newton's law of cooling, but I think we'll do that next class.